Okay, let's have a look at our first lecture. So we'll have a look at these important elements. Especially we're going to have a look at matter, elements, atom, mass number, atomic number, isotopes, and the composition then of atoms, with protons, neutrons and electrons being the I guess the first discovered components of atoms. The relative atomic mass then, and um, how you see numbers on the periodic table that have decimal points on them, and I will illustrate that. Then you go into a bit more detail with atomic orbitals and electronic configurations, looking at atomic orbitals and how electrons are distributed through an atom then. And then the rules that govern, there's the Pauli exclusion, the Aufbau principle, and Hund's rule, which determines then how electrons will fill the shells or the orbitals on atoms as you move across and down the periodic table. And then we move down to the electronic configurations to the shells. We look at isotopes or ions, the cation and the anion, and then electronic configurations of simple cations and anions. So we're going to have a look at that right now, because that is the composition of lecture 1. Okay, I've zoomed into the periodic table, and you can just see there, looking at the different elements, hydrogen and lithium and beryllium. You can see that you've got the decimal numbers that I spoke about just a moment ago. For lithium then, the relative atomic mass is 6.941, beryllium 9.012. So we're going to be looking at, how do we end up with decimal values and not just perfectly whole numbers. We're going to look at that. We're also going to look at this element up here, where you've got 2 and 2 and 2 and 1 and 2, 8, 2, and the consequences of that and other aspects. Okay, so if I briefly look at the 3 topics right here, matter, elements and atoms, we can briefly just cover them. So for instance, it says down here that matter is anything that occupies space and has mass. All matter is made up of elements. And of course, the periodic table is composed of these elements, the elements being the likes of boron, carbon, nitrogen, oxygen, fluorine, etc. Now, the difference then between an element and an atom, of course, is, okay, the element is oxygen, which is O, but in an atom it exists as 2 oxygens bonded together. So the atom of oxygen is O2. So it consists of 2, if you like, 2, well, it's the element oxygen. So again, the periodic table is composed of all of these individual elements. And matter is composed of atoms, atoms being the building blocks or the smallest units that matter is made of. And what I meant to say was that an O2 would be a molecule of 2 atoms of oxygen forming O2, which would be a molecule. So essentially this is the point, that elements determine the atoms, which when they bond together make molecules, and then the molecules themselves are what matter is composed of. And so I just finish off that schematic with matter. So for instance, you breathe into a balloon, let's say, for example. Yeah, there's going to be a number of different elements. There's going to be water vapor, there's going to be oxygen, there's going to be some carbon dioxide, etc., being exhaled into the balloon. Okay, so the point about it is that if we pick on the oxygen, for instance, we're saying now that the element oxygen is going to be in the balloon. Okay, but if we want to quantify, okay, we've just labeled it, the element is going to be, yes, there's going to be oxygen in the balloon, but if we want to quantify how much oxygen is in the balloon, that's when atoms become relevant. And the amount or the quantity of oxygen that would be in the balloon would be the number of atoms at its simplest level. These are the building blocks of what would be a constituent within that balloon. So I just color coded that concept, that the element is oxygen, the atom is O, but the molecule consists of 2 oxygens to make up a molecule of oxygen, and I've just denoted the O with the 2 beside it then to show ultimately the molecule is O2, but the balloon is composed of matter which is partly oxygen O2 and carbon dioxide, as I said, and water vapor, etc. Okay, next we're going to look at the mass number, atomic number and isotope, and I'm very conscious of the time that you have for each one of these videos. It's 10 minutes is the limit, so I am going to put a diagram together and we're going to discuss these 3 areas: mass number, atomic number and isotope, and we'll build in this next part here: protons, neutrons and electrons, and the periodic table will also incorporate that. For no particular reason, we'll have a look at the sodium, the element sodium, and we will look at these areas: atomic number and mass numbers. So for sodium, we're interested in these 2 numbers, this number and this number right here. This is called the atomic number, it's 11, and this is the mass number, 22.98. So I just included the chemical symbol for sodium, which is Na, and we've got the number 11 here and the number 22 here. The 11 refers to the atomic number, which is the number of protons, P for protons. The mass number, you see, is the number of protons plus neutrons when they're added together. So that's the mass number and that is the atomic number. You don't see any mention of the electrons in the mass number because the electrons have a very small mass in comparison to the proton and the neutron. By comparison, an electron has a mass of 1/2000th the mass of a proton or a neutron. So that's the reason for that. That's why you don't see the mass of the electron included in the mass number. So it follows from the above example then, if you're trying to find the number of neutrons, then from the above example, you've got your mass number and you've got your atomic number, and the difference between them, of course, is you've got protons in both of them, but you've got neutrons in this one. So to get the number of neutrons is very simple. You just take the atomic number away from the mass number. Now, which in our case, mass number is 22 coming from here, atomic number is 11 coming from here, and by subtraction you get an answer of 11. That means there's 11 neutrons in a sodium atom. Now, I've just made mention of the word isotope, and an isotope is the same element, but it has different numbers of neutrons, so its mass number then by definition changes. Okay, so you've got things like carbon 12, 13 and 14 would be examples of isotopes of carbon, where the carbon element consists of different numbers of neutrons, and they are called isotopes of carbon and other elements as well, which I've just listed below then. Isotopes of carbon being carbon 12, carbon 13 and carbon 14. And this brings us really conveniently to relative atomic mass. Now, I said that this is the mass number down here, but you see the decimal points, and I said this at the very beginning of the tutorial, that it isn't just a straight 24, it's 24.305, which is rounded off as 24.31. So the point about that is well, how does 24.305 appear then as the relative atomic mass? So we'll refer back to the tutorial notes for that. You see, it's down to natural abundancy, so it's abundancy in nature. Magnesium 23.99 or 24 is 78.7% abundant in nature. And so too for the other times that magnesium exists in nature, its abundancy. And if you work out for 100 atoms then, by doing this example here that I've color coded for the first one, and you work down through it, you work out then by dividing by 100, because you've had 100 atoms. If you divide by 100, you get the average mass of one atom, which of course turns out to be 24.31. 24.31, which is the exact same number that we see on our periodic table, 24.305. And that's how the relative atomic mass, due to abundancy in nature, occurs and is worked out.